Okay, so for today's video lesson, we're going to be doing the chain rule. Okay, so the chain rule, this is going to just one of our other rules that's going to allow us to differentiate functions a little bit easier. Okay. Yeah, so if you guys want to find the proof for this, it's kind of beyond the scope of this course, but the proof is on page 58 to 61 of the module workbook. Okay, but for the purpose of Math 31, we just need to know how to use a chain rule. Okay, and I don't want you guys to freak out or anything. I will give you guys the chain rules on a quiz or a test. Okay. All right, just gotta clean that up. So so the chain rule is, so if y is equal to a composite function, just in general, f of g of x, that is a polynomial with an exponent other than 1, okay, then the derivative of y with respect to x is equal to the derivative of y with respect to u. Oh. Multiplied by the derivative of u with respect to x. So I remember we had a question earlier when we were starting to introduce derivatives and stuff like that, and it was about this notation here. So when we take the derivative of just like a function, let's just say we had a function y is equal to 2x minus 1. So when we take the derivative of y here, so because it is y is equal to 2x minus 1, that's where the dy on the top comes from. And because in here, the variable is x, that's how we're taking the derivative of y with respect to x. Okay, so in this case, it would just be 2, right? The derivative of 2x minus 1 will just be 2. Derivative of a constant is 0. Okay, now for this rule, for the chain rule, when we do the derivative of y with respect to x, that is going to be equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. Okay, and we will get into that a little bit here. We're kind of familiar with the v and the u from yesterday, right? So this is going to be kind of related to that as well. Okay. Yeah, so let's get into an example. So that is the chain rule right there. Okay. Okay, so example 1, we're going to differentiate y is equal to 2x minus 1 to the exponent 10. So for this, we're going to say u is equal to 2x minus 1. That's what's in the brackets there. Okay, so our formula here is u is equal to 2x minus 1. So if we take the derivative of u, we will be doing that with respect to x, because x is our variable in this formula, u is equal to 2x minus 1. Okay, so the derivative of u with respect to x is just going to equal 2. Sorry, that line's kind of annoying. Okay, it's just going to equal 2. And then, so u is equal to 2x minus 1. So we can rewrite our y formula as y is equal to u to the 10. Okay, so we're just kind of substituting that 2x minus 1 for u. Now, if we were to take the derivative of y, because u is our variable in here, we're going to be taking it with respect to u. Okay, so the derivative of y with respect to u, so we'll apply the power rule to the u10. So it'll be 10u and then subtract 1 from the exponent. It'll be 10u to the 9. Okay, hopefully that makes sense to you guys. Okay, so as per the chain rule, so dy over dx is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. Okay, lucky for us, we've already found the derivative of u with respect to x, and we found the derivative of y with respect to u. So now we can just go and multiply those two terms together, okay? So dy, so derivative of y with respect to x is equal to 2 multiplied by 10u to the 9. Okay, so we can just multiply that together. So that will equal 20 times u to the 9. Now, if we were to differentiate this term right here, 20u to the 9, we would be taking the derivative of y with respect to u. But we want to take the derivative of y with respect to x. So we need to substitute in our u for the 2x minus 1 like we did at the top, okay? So dy over dx is equal to 20 times 2x minus 1 to the 10. Okay, so notice that our variable in here now is x. So if we're taking the derivative of y, this will be with respect to x. Okay. At this point, this is fully simplified as we get. So now we can kind of rewrite this as y prime, which is the same thing as saying the derivative of y with respect to x. Y prime is equal to 20 multiplied by 2x minus 1 to the 9. Sorry, and there should be a 9 here. Okay, so that is our first taste of the chain rule. Do we have any questions with that right away? Perfect. Okay, so same kind of thing here. So our function or whatever we have in the brackets is going to be our u. So u is equal to x squared minus 2x. So therefore y is equal to u to the 5th. Okay, so same thing like we did last time. We'll take the derivative of u with respect to x. So that will equal 2x minus 2. And if we take the derivative of y with respect to u, because u is our variable, it will be 5u to the 4. Okay, as per the chain rule, the derivative of y with respect to x is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. Okay, we've already found dy du and du dx. So we can just substitute this in. We have 5u to the 4th. So the 5u to the 4th multiplied by 2x minus 2. At this point here, we need to substitute in our u for the x squared minus 2x because we want to take the derivative of y with respect to x. If we did it right now, it would be the derivative of y with respect to u. Okay, so dy over dx is equal to 5 times u, which is x squared minus 2x to the 4th, multiplied by 2x minus 2. So at this point here, because we've already taken the derivative of u with respect to x and the derivative of y with respect to u, to present our final answers, we can simplify this a bit further. Okay, so 5 is outside. Within this term here, we have x is common in both terms. So we will factor out an x, which will leave us with x minus 2. And that will be to the 4th. And on the second term here, we can factor out a 2. And then that will leave us with x minus 1. Okay, we can further simplify this. I'm going to distribute the exponent 4 into the brackets. So we will have 5 multiplied by x to the 4 multiplied by x minus 2 to the 4 multiplied by 2 multiplied by x minus 1. Okay, we can further simplify this. So we can multiply the coefficients. So 5 times 2 is equal to 10. X in the brackets, the exponent 4 will just be x4. We will leave x minus 2 to the 4 and x minus 1. And we are happy with that. So to put our answer in a final term, so y prime, the derivative of y with respect to x is equal to 10x to the 4 bracket x minus 2 to the 4 bracket x minus 1. Okay. Any questions? Excellent. Okay. So this one is going to look a little bit different, right? Y, we have a fraction here. So y is equal to 1 over 3 minus x. We can actually rewrite this. So my palm's getting in the way all the time. We can rewrite this as 3 minus x to the exponent negative 1. Okay, so that might look a little bit easier for us. So whatever's in the brackets will become our u. So u is 3 minus x, and therefore y will become u to the minus 1. Okay, so we'll take the derivative of u with respect to x will equal negative 1, and the derivative of y with respect to u, so we're going to take that negative 1, put it out in front, negative 1u, and then subtract 1 from the exponent, so negative 2. As per the chain rule, dy over dx is equal to dy over du multiplied by du over dx. So we'll just substitute these in now. So we have negative 1 u to the negative 2 multiplied by negative 1. That will give us positive 1 u to the negative 2. Okay, at this point, we will substitute in our u for our 3 minus x. Okay. And we do not like negative exponents, so we will rewrite this as 1 over 3 minus x to the 2. Okay. All right. So same kind of thing here. We have an ugly looking function, maybe to some, but we just need to remember here that anything under a square root is to the exponent 1 over 2. Okay, so we'll just rewrite this as negative 3 over 5x plus 3 to the exponent 1 over 2. Okay, and then we will rewrite that as negative 3 times 5x plus 3 to the exponent negative 1 over 2. Okay, so whatever is in that brackets again will become our u. So u is equal to 5x plus 3. And therefore, our y is going to equal negative 3u to the negative 1 over 2. So like we've been doing, we'll take the derivative of u with respect to x. So that will just be 5. And the derivative of y with respect to u. So we take that negative 1/2 and multiply it out front. We will get positive 3 over 2 u, and then we'll subtract 1 from the exponent. So we'll get negative 3 over 2. So as per the chain rule, dy over dx is equal to dy is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. So derivative of y with respect to u is 3 over 2 u to the negative 3 over 2 multiplied by 5. Okay, so if we do that, 5 multiplied by 3 over 2 will give us 15 over 2 u to the negative 3 over 2. At this point, we will substitute in our u, which is 5x plus 3. All right. Now we have a negative exponent, which we do not like. So we can rewrite that. I'm just going to go to the left here. And we also have a denominator, so we can clean this up a little bit. Like, so 15 will be our numerator over 2 times 5x plus 3 to the exponent 3 over 2. So like we had at the beginning, if we're taking the square root of a number, the exponent is 1 over 2. So in this case, we can rewrite this. So this would be okay right here. But we could be better. So we'll say 15 over 2 multiplied by the square root of 5x plus 3 to the exponent 3.
Mr. Jones,
Yep.
when we multiplied 15 over 2 so that it was in the fraction, why did like all the other stuff go on the bottom?
Oh, like the 2 and 5x plus 3?
Yeah. Like why isn't it multiplied on the top with the 15?
Yeah, no, good question. Because that the negative 3 over 2 exponent belongs to that u, or to the 5x plus 3. Right? So when we fix that so it has a positive exponent, that will come along with it into the denominator.
Oh, okay. Okay, sweet.
Yeah, good, really good question. Really good question. Okay, so yeah, there are going to be a couple ways that we could write this, and always try to put it in your best way. But if you leave it in this form, I will still give you marks for that. Okay. Cool. Okay, now that we have explored the chain rule enough, we can talk about a chain rule shortcut. So if we have a function where it's y is equal to u to the n, just in general, then y prime, or the derivative of y with respect to x, will equal n. Oh. So I need to equal n times u to the n minus 1 multiplied by whatever is in those brackets. So multiplied by the derivative of u with respect to x. Or if we have a function where f of x is in the brackets and then n is outside of it, same kind of thing. Y prime is going to equal n multiplied by f of x, n minus 1 multiplied by f prime of x. And remember, f prime of x will just be the derivative of f of x. Okay. So let's apply these here. So if we have in here, so we will say our u will be 3x squared minus x. So u prime, or if we just take the derivative of u with respect to x, will give us 6x minus 1. Okay, so y prime here is going to equal 7. So we're just going to bring that power out front. Going to leave u alone. Subtract 1 from the exponent, and then multiply that by u prime, or the derivative of u with respect to x. So multiply by 6x minus 1. Okay, so this saves us kind of like the u substitution step that we've been doing. Okay, so for this, we can simplify our terms. In the first one, x is common in both. So we will factor out x, which will leave us with 3x minus 1 to the 6. And we'll just have 6x minus 1 here. Now we can distribute that 6 exponent into those brackets. And then we can further simplify that. So we'll get 7x squared final answer. So it's going to save us a little bit of time because we're not substituting in, like, once we say that u is 3x squared minus x, we're not differentiating y again by substituting in the u to the 7, right? So this will just save us a little bit of time. Like, Mr. Jones, why do you show us the shortcuts after we do it the long way so many times? Okay, so let's rewrite this so it's a little bit more friendly for us. So anytime there's a square root, it's to the exponent 1 over 2. So 3 over 2x minus 1, exponent 1 over 2. And we can rewrite this as 3 times 2x minus 1 to the negative exponent 1 over 2. Okay, so when we do this, we are going to leave that 3 alone. And then we'll multiply that by the derivative, like we'll take the negative 1 over 2 and put it up front. We'll leave the 2x minus 1 alone. And we'll subtract 1 from the exponent. And then, as per the rule, we're going to be multiplying that by the derivative of whatever's in the brackets. So the derivative of 2x minus 1 will just be 2. And now we can go ahead and clean this up a little bit. So we'll multiply our whole numbers, so it'll equal 6. And then we have negative 1 over 2, 2x minus 1, just want negative 3 over 2. We can, again, multiply our whole numbers out front. So 6 multiplied by negative 1 over 2 is negative 3, bracket 2x minus 1, negative 3 over 2. And hopefully you're saying we have a negative exponent. We do not like that, Mr. Jones. I would say excellent. So we'll leave our negative 3 on top. And then our 2x minus 1 will come to the bottom, but with a positive exponent, 2x minus 1. Okay, so that would be good. Or if you wanted to, you could do y prime is equal to negative 3, and you could put that into a root. Okay, let's give you a second there. Okay, so for this next question here, we're going to do an application using the chain rule, okay? So we can actually use the chain rule for real life purposes, okay? So our example here, we have a baseball that is being hurled at a speed of 30 meters per second at an angle of 30 degrees to the horizontal. So this is like kinematics in physics 20, right? So it's gonna look something like this. Goes at 30 meters per second at 30 degrees to the horizontal. So if we wanted to plot this on a graph, like really crudely, if we had h on the y-axis and x, so in our variables here we have h is in meters, and that's going to be our height, and x is our horizontal distance. Okay, so as it's thrown, its height is going to go up, and then of course it's going to come back down eventually, right? So that is what that kind of looks like. At any time, the height of the ball is approximated by this formula here. So h is equal to 15t minus 5t squared. Okay, and then its distance at any time can be measured by the formula x is equal to 26t. So the question is asking, determine how fast the height of the ball is changing with respect to its distance from you. Okay, so our variable h, so how fast is the height changing with respect to its distance? So is what it's asking for us. We are looking for the rate at which the height is changing with respect to the distance. Okay, that's what it's asking. How fast is the height changing with respect to its distance? Okay, so I'm actually going to show you two methods to solve these problems. Okay, so method one, we are going to kind of like use our product rule. So, or the chain rule, sorry. So the derivative of h with respect to x is equal to the derivative of h with respect to time multiplied by the derivative of time with respect to x. Okay. So,
Mr. Jones,
yes.
how do you know where to put like the different variables?
Yes, really good question. So in this question in particular, it's just asking like how fast is the ball changing with respect to its distance. Okay, so today I really tried to emphasize like the derivative of h with respect to t for leading up to this question. Okay, so just by reading it, determining how fast the height of the ball is changing with respect to its distance from you. So we're looking how h is changing with respect to x. Did that answer your question? Or are you talking about like at this point here for method 1?
Yeah, like for method 1.
Okay, yeah, really good question. So this kind of like so if we jump back to, sorry, I'm just touching papers, but I'll just use my computer. So if we jump back to this slide here, so we know the derivative of y with respect to x is equal to dy over du multiplied by the derivative of u with respect to x. So it's just like changing the variables of that chain rule. Okay. If you were given a question like this, I will give you this setup right here.
Okay, sounds good.
Yeah. But really good question. Good question. Okay. So we know h and we know x, right? We've already isolated that, or we know the formulas for those, right? So if we wanted to take h prime, so if we took the derivative of h, because h is our formula, h is equal to 15t minus 5t squared, and t is our variable, h prime is going to be, so we're taking the derivative of h with respect to time, because that is our variable. Okay, over here for x is equal to 26t, we're taking the derivative of x with respect to time, because time is also our variable there. Okay, so h, hopefully we are all good up to that point, and if not, just save your questions for the end. I'd be more than happy to go over this with you guys. Okay, so h, as we said, is 15t minus 5t squared. So if we took the derivative of h with respect to time, because time is our variable in there, right? And h is our formula. So the derivative of h with respect to t would be 15 minus 10t. Okay, and because right here, I'm going to use a different color. Right here, we have x is equal to 26t. If we took the derivative of that as is, we would be taking the derivative of x with respect to t. But what we need here is the derivative of t with respect to x. So if we manipulate, again, this formula here, sorry for all the red arrows, so that it writes t is equal to whatever, that is when we would be taking the derivative of t with respect to x. Okay, so if that was a little wordy, I'll just show you what I mean here. So we have x is equal to 26t, but we want to take the derivative of t with respect to x. So let's isolate t. So we'll divide both sides by 26. Okay, so now we know t is equal to x over 26. So if we now we can take the derivative of t with respect to x, because x is the variable in our equation. So derivative of t with respect to x, if we take the derivative of just an x, it will be 1. Okay, and we leave the denominator alone here. I know when we differentiate constants, it turns into 0. For this particular problem, we're going to leave that alone. We're just differentiating the variable. Okay. So as per our chain rule, I think you guys are probably sick of me saying that. We know, so I just got to move my. Okay. So if we take the derivative of h with respect to x, it is equal to the derivative of h with respect to t multiplied by the derivative of t with respect to x, which we have found. Okay, I am running out of space on this slide, so I'm going to just move over to where we would do method 2, and we're just going to do method 2 on a different page, okay? So yeah, so the derivative of h with respect to t we found is 15 minus 10t, and the derivative of t with respect to x is 1 over 26. So we'll just multiply those together. Okay. At this case here, hopefully you're saying, Mr. Jones, we have a t as our variable in here, so we can't take the derivative of h with respect to x. Awesome. We know that t is equal to x over 26, so we can substitute that in now. So that's dh over dx is equal to 15 minus 10 multiplied by x over 26 multiplied by 1 over 26. Okay, so if we simplify that, we will get 15 minus 10x over 26 multiplied by 1 over 26. And if we multiply that, derivative of h with respect to x. So 15 multiplied by 1 over 26 is equal to 15 over 26. And 10x over 26 multiplied by 1 over 26 will give us 10x over 676. Okay. And we can actually reduce that one more. Over 26. If we reduce our fraction here, dividing it by 2, we'll get 5x over 388. So this is how fast the height is changing with respect to its distance. So where that, depending on where the x is, we can find the height in that formula. That is the rate of change for the height and its relationship to its distance. Okay, so I'm going to show you another method to do this. So method 2, we need, so as the question is saying we need the derivative of h with respect to height. So we can write h in terms of x. So what does that mean? Well, we know, oh no. Sorry about that big line. I'm just gonna write that again. So we need dh over dx. So write h in terms of x. So we're given the two equations. H is equal to 15t minus 5t squared. And we're also given, we were given x is equal to 26t, but let's manipulate that, and which we already did. So t is equal to x over 26. And if we do it that way, now we can substitute in our t where we see it in here. Okay, so h is equal to 15 multiplied by x over 26 minus 5 times x over 26 to the 2. Okay, we can simplify this. So h is equal to 15x over 26 minus, so if I put the square in here, it'll be x squared, 26 squared is 676. So we will get negative 5x squared over 676. Okay. So if we now at this point, because our formula is written in terms of h and x, right? We have h is equal to 15x over 26 minus 5x squared. So now we can take the derivative of h with respect to x. Okay, so the derivative of 15x is just going to be 15 over 26. And the derivative of 5x squared will be 10x. And we're just deriving the numerators. Okay, and then again, like we did, we can reduce this 10x over 676 by dividing by 2.
Mr. Jones,
Yep.
I have to go early, so is it okay if I just watch it later?
Yeah, totally. We're actually done after this now. So
Oh,
you are totally fine to leave.
okay. Thank you.
Okay, no worries. Okay, so I'm just going to do a final therefore statement. And then if you guys have any questions, I would be happy to answer them then. Okay, so therefore, the height of the ball is changing at a rate of 15 over 26 minus 5x over 388.
And
All right.
that's meters per second, is it?